Okay, today we're doing a little bit of practice for the final in Precalc. And I believe it's day 4 of the review. It's the last session that we have. And I'm going to be starting in the neighborhood of problem 44 in the packet. But we're still reviewing 43, which was about identities. So we started with this kind of a problem. We replaced cosine squared with 1 minus sine squared. And then 1 minus sine squared we replaced with the factored form of that. 1 minus sine and 1 plus sine. Look at these. Okay. And then you can see where these two canceled. One on the top, one on the bottom. The answer was 1 plus sine squared. Let me give you another one like that. Sine squared theta minus 1 over sine theta plus 1. Solve. Actually, I should say simplify. All right, so this one's factoring again. Sine theta plus 1 and sine theta minus 1. And plus 1 part cancels. You should have had sine theta minus 1. In this case, it is minus. Any questions about that? All right, some other little things. Just little quick stuff. Have this pattern memorized yet? What's the answer to that? 7. Good. Answer 0, because I have 1 in the argument. Got a 1 in the argument spot. Yeah, nothing. Okay. Another little quick one. Sine squared plus cosine squared. What's that equal to? 1. Wherever you see that in the problem, you can replace it with a 1. Okay. So if it was like this, you'd have a 1 on the top, and then it's 1 over tangent, and then what's tangent? What's 1 over tangent? Cotangent. Final answer on this would be cotangent squared. Okay. Let's do another couple. One with the coat is cosine. All right. So, given that, what's cotangent? There's 2 things you can say about cotangent. Please write them down. What's cotangent squared? There's several options. In fact, I can think of 3. There's always 1 over. Every single function there is has a 1 over function that goes with it. Let's start with that one. Thank you. Then there's often an identity that's that goes with it. That's maybe for the squared one. That's a part of a little snappy saying. In this case, it's 1 with the coat is cosine. And cotangent, then, we just take this 1 and move it to the other side. It'll be cosecant minus 1. Cotangent is cosecant minus 1. Yes. It would be wrong. Yeah, you got to have the squared there, otherwise it's a totally different thing. And since it is squared, we could factor it. Cosecant plus 1, cosecant minus 1. Okay. No, you don't have to write all of this. It's just, these are options to put instead of this. And the last one I can think of is tangent is sine over cosine. So it's cotangent. Cosine over sine. Because tangent was sine over cosine. Cotangent is the flip, and therefore it's cosine of sine. All right, so there's a lot of different options. Next one, write down what you think sine of 2 theta is not on your sheet, which you'll get. You'll get a sheet with a few things on it, but that's not one of them. Sine of 2 theta. So a typical question might be, you'd have to know, oh, I know what it is. How many of you are confident you know what sine of 2 theta is? Seriously, only 3 people? 4 people? Okay, you got some stuff to memorize, I guess. 2 sine theta cosine theta. All over sine theta. Because of this part. This is just equal to that, but sine theta was already there. And so now I can cancel sine thetas. Final answer on that one, 2 cosine theta. Is 2 cosine theta the same as cosine of 2 theta? No, different. Cosine of 2 theta has 3 different complicated things. We don't make you memorize that one. Cosine of 2 theta, when you see it though, like you probably will see it, you see that on your test, you go, oh, I better look at the front of the packet and find, they'll go give you a sheet. I better look at that sheet and I better find those things because I can substitute them in. Okay. Next, let's go back to the packet. I think we've done enough practice on identities. So if I find your packet, and this happens to be problem 42 that I'm in. Part D, just a quick reminder, something like that. That's another type of identity. That's the cofunctions one. So what's the cofunction for sine? Cosine. So that would be replaced with cosine of y. And then it's secant times cosine. Another strategy I want to remind you about, change everything into sines and cosines. It doesn't always work, but sometimes it works really well. Like secant, secant's really 1 over cosine. So now it's, this one turns into 1 over cosine times this one's cosine, and I can always put it over 1, and then those will cancel out and it'll be easy peasy. Right? This is another good one for make everything into cosines and sines. This is another good one for make everything into cosines and sines. So, all right, moving on. We did some of these already. Use the sum or difference identity, but we didn't get very far on ones that you had to use the sum or difference identity that are like this. My suggestion to you is to take those and change them into degrees. That's always worked best for me. Okay, so let's do this one over here just because the numbers are a little nicer to go a little quicker. 7 pi over 12. How do I change that into degrees? I multiply by either 180 over pi or pi over 180. You look at the stuff you have in it. Do you have degrees that you want to cancel, or do you have pi that you want to cancel? Pi, so therefore you put the pi down there, and therefore it's 180 on top. And now I go cancel, cancel, and then you got to do a bunch of reducing. Everybody simplify that down and tell me how many degrees this turns out to be. Cosine of some number of degrees that I want you to figure out by reducing. Give that one a shot. Six does. 6 goes in here twice. 6 goes in here not 3 times, but 30. Then I have 7 times 30 over 2. Is there a way to make that even easier? Yeah. But I could reduce the 30 and the 2. But I could just do 7 times 30 is 210 and divide it by 2, and it'll be half of 210. That's not too bad. What's that? 105. So apparently, this is the same as cosine of 105. Great. How am I supposed to do that since there's no calculators on the test? You're supposed to make it a sum or a difference. I think you know that you're not going to be subtracting 2 numbers and making it equal to 105. Since your only options are things you know how to do in your head are things like cosine of 30, 60, or 45. So using these 3 numbers, how do you make 105? 60 plus the 45. Good. So this becomes, instead of cosine of 105, I make it cosine of 60 plus 45. Now I've got a sum, and now I got that formula on the front of the packet that tells me what to do. Do you remember on cosines that it goes plus minus at the beginning of the formula and minus plus at the end of the formula? That means they reverse the sign. So I need to have a minus sign in my answer. And if I remember right, it's cosine, cosine, sine, sine. Do I have that pattern right? Is that right? Okay, good. And then I just have to put in 60 and the 45 and the 60 and the 45. Those are all degrees. Notice I'm doing this whole thing in degrees, even though it started in radians. But when you're all done, in my opinion, right now, if we had used radians right there, it'd be harder because I'm going to refer to the 30, 60, 90 triangle because it's got a 60 in it. If we were using pi over 3 right there, you'd have to go to the pi over 3 triangle, and I don't know what that is even. So 30, 60, 90 triangle makes sense to me. And that's a 1, 2, square root of 3 triangle. And therefore cosine of 60, cosine's adjacent, hypotenuse, 1/2. 1/2 times cosine of 45. Need a different triangle for that one. Here's the parent triangle for the 1, 1, square root of 2, 45-degree angle. Again, would you call that the pi over 4 triangle? Doubt many people do that. So I'm going to use cosine of 45 degrees, cosine adjacent, hypotenuse, 1 over root 2. And then I subtract it from, and I have to keep going like that and get these two answers all done with those little reference triangles. Okay, so that's a reminder on that section. Number 44. This is one of the tougher ones. Now, I don't want to take away all your fun of solving this, but I will give you a little bit of advice. One of the options is to factor that, but, and it might look like, oh yeah, then I can cancel the thing on the bottom with the other thing. It won't work. Because once you got it factored, it's 1 plus tan and 1 minus tan, and this is tangent squared on the bottom. So you cannot factor that top and make it cancel the bottom. So factoring, I'll save you some time. That was a bad idea. But what you can do is say, what's something else tangent can be? Tangent squared. Secant. 1 with the tan is what we seek. 1 plus tan, seek. And so 1 minus tangent, wait a minute, that's not the same as secant. See what I mean? 1 minus tangent. Okay. So that one doesn't work. Could I replace tangent, though, with secant minus 1? See what I mean? Isn't tangent the same as secant minus 1? Not the 1 minus the tangent, but couldn't I replace just the tangent right here with secant minus 1? Yes, I can. So it's 1 minus secant minus 1 all over 1 plus tangent. And you might be saying, oh, don't know where this is going. It's okay. Let me simplify it a little bit. This 1, this negative gets distributed to both things. This becomes 1 plus the other 1 makes 2 minus secant squared. 2 minus secant squared. All over 1 plus tan. Well, 1 plus tan, I had that before, remember? Up here, 1 plus tan is what we seek, right here. So I can replace the bottom one, the 1 plus tan, I can replace that with a secant because of this fact right here. So I'm going to say I'm going to replace that with secant. And you just keep playing with it until you finally get it to be equal to cosine of 2x. Well, what is cosine of 2x? It's got several different choices. Nope, this negative right here, it was a 1 minus tangent squared. So I need a 1 minus and then secant squared. And then this negative gets distributed. That is a minus. So really what you're asking is, does 1 minus secant squared and then minus 1, does that really equal what I said it equaled, which is right there? That's the part you're questioning? Okay. That's okay. You said that before, and I'm just trying to make sure you get why I'm doing it the way I am. So that is like a negative 1 in front, which gets distributed to both. So that's like negative 1 times the secant squared. That secant squared is negative. So it needs this negative right here on the secant squared. It does. Really. I'm glad you checked me because you know I make plenty of little mistakes, so this is not one of those things. Yes. You don't get how you get 2? Okay. Let's just actually distribute this out. Negative 1 times the secant makes negative secant squared x. Negative 1 times negative 1 makes positive 1. Right? Now I already had a positive 1 at the beginning. Right? What's 1? That's 1. 2. There we go. So this is 2 minus secant squared. I know, you're looking at this probably saying, how can I do anything with that makes it any better? There's a way. To begin with, if you have something that's that was 2 separate fractions, you would probably want to add them together and get a common denominator. This has already got a common denominator. It's already together. So you can try breaking it up. This is 2 divided by secant squared and negative secant squared divided by secant squared. Sort of like if I had 2 plus m all over 2. Do you get I could break that up into 2 over 2 plus m over 2? We can break this big fraction that's got a common denominator up into its 2 separate parts. Okay, well that's what I'm going to do here. I'm going to take this 2 and divide it by secant squared. And then I'm going to take the other part, negative secant squared, and divide it by secant squared. And that is equal to what? 1. And then this secant squared on the bottom, I could replace with a 1 over cosine. Secant is 1 over cosine, right? Then what will I have? I'll have 2 over 1 over cosine. And this one's just 1, so minus 1. And then this you flip and multiply, and you'll end up with 2 cosine squared minus 1, and that's exactly what cosine of 2x is. Cosine of 2x had 3 options of things you could replace it with, and that's one of them. I did it a completely different way in a different class, but this is the way it's done on the key, so I thought I would try to explain the one that was done on the key. Yep. I know. It's long, it's complicated, but this answer is also shown on the key, and I don't want to spend half an hour on one really hard problem and do it twice. I will show you how to do it one other way. Okay. So, remember the rule about changing everything into sines and cosines? So I could do that. And I'd have 1 minus, and tangent is really sine over cosine, all over 1 plus sine over cosine. Please don't chat right now. Okay, now, in order to move to the next step, I would have to get a common denominator, and this way is going to go really slowly and painfully. So I'm gonna do kind of a hybrid of the two. So instead of changing everything to sines and cosines, I'm going to change the top to sines and cosines. I'm going to take the bottom, and I already had something clean for that, right? That was one of the identities. 1 with the tan is what we seek, right? So I'm just going to put a secant there. Now secant, I could replace with sines and cosines. See what I mean? What's secant going to be in terms of sines and cosines? 1 over cosine. Now, when you have a fraction over a fraction, it's just begging you to flip and multiply it. So I take this top part here, and instead of dividing by all of that, I'm going to multiply by, flip it, cosine over 1, and then this is gone, and I'm going to take cosine times 1, is cosine, and cosine times this, the cosines will cancel, and it's just sine. And that's one of the other things that cosine of 2x is. It's cosine squared minus, there's the minus right there, and once you multiply it in here, you'll have sine squared. It'll be cosine squared minus sine squared. That's one of the other things that cosine of 2x is. I know, this is tough. This is like some of the hardest pre-calc that there is. It's trig. Did you know that there used to be a full year of trig? Like the class was called trig, and that's all you did all year. Yeah, we just did it for 1 quarter. We've narrowed it down a little bit. But you used to go even further than this on trig. It used to be, this is still one of the harder questions, but you'd have a whole year and that'd be the hardest question. So when we narrowed it down to only 1 semester of trig, you obviously have to still get to the hard stuff. It's just, you didn't have a whole year to learn it. Okay, I want to feel better about it. That's fun. All right. We need to move on. We spent a lot of time on 44. So now, 45. These are just, I hope you recognize the pattern. A lot of math is just recognizing patterns. And so I recognize that this is sine, cosine, cosine, sine. It's just these are backwards. But it's a multiply problem. Can't I just reverse them? Yeah, you can. So this is sine, cosine, cosine, sine. I've seen that before. In fact, it's on the front of your packet. It's one of those patterns that we give you. Is it sine or is it cosine? That gives you an answer that's sine, cosine, cosine, sine. Sine. So this must be sine of something. And I just got to figure out what got added. Not too hard. The little pieces parts, the little angles that got added, this is where the angles go. They're here, and here, and here, and here. And they're all pi's over 5 and pi's over 2. Pi over 5 and pi over 2. And there's your answer. Could reverse that, and I bet just fine. Adding is commutative. You can rearrange it. Okay. Commutative might not be the right word. My brain's locking up, but you can reverse and say like 5 plus 2 is the same as 2 plus 5. All right, now the other one is cosine, cosine, sine, sine. That's a different pattern. That's not the one for sine. If you look on the front of your sheet, which one is cosine, cosine, sine, sine? That's cosine. And do you remember that on cosines, the original problem here is either an add or a subtract based on what the other one was. The rest of the problem was a minus, then it must have been a plus. These are opposites on the cosine rule. So then I just got to figure out what 2 things get added. 7, 3, 7, 3. Looks like 7y and 3y. Can I actually add those together easily? Yes. Might as well just say cosine of 10y. Okay, this next part depends on you knowing those factoids, like sine of 2 theta. It's 2 sine theta cosine theta. And then you subtract 2 sine theta from both sides. And you'll end up having something equal to 0 that you can factor. And it'll factor into 2 parts. Cosine of 2x, I don't know. Got to look it up in the sheet. We just solved it. But I think it was cosine squared minus sine squared. Right? That's one of them. Another option is, instead of that, I could have put in 2 cosine squared minus 1, I think. Isn't that one of them? You guys have the sheet, I don't. I don't remember what cosine of 2x is. Is it 2 cosine x minus 1? Is that one of them? Okay, thanks. And the reason I like that one is because now it matches the other side. They both have cosine on them. So once again, you look to factor it, and I can't factor it until I move this to the other side, but I subtract cosine x from both sides, and then I can factor it. Once you've got it factored, you have two things set up, times each other, equaling 0, then get this equal to 0, and set that equal to 0 separately. All right, we're getting there. Let's move on. Number 47 is incredibly easy if you know what sine of 2 theta is. If you've memorized it, did refer to it earlier. Okay, number 48. Is it growth or is it decay? Right away I look at this and I say, oh, it's a decimal, it must be decay. I'm wrong. There's often more to it. What does this one have that makes it look like it's decay, but then it's not really decay? The negative exponent, and that means you flip it. And so instead of 75 over 100, which is how it started, to the negative x, then that negative power comes in and flips it and makes it 100 over 75, and you can tell that's bigger than 1, and therefore it's actually growth. Watch for the negative exponent. They'll do that. I don't even know for sure, but I would really expect them to do that because we did it on the test. So you're thinking it's decay, but it's really growth. Once you know it's growth, you can just make a quick sketch and go, okay, generally it's doing this, and I want to write limits. The left-hand limit, lim of the function, as x approaches negative infinity. And that's way, way, way that way. And it gets closer and closer to what? Come on. Help me out. The limit is it goes way over this way. Negative 0, did I seriously get that? 0. Yes, I agree. Okay. And then, on the way right side, way this way, lim of the function as x approaches infinity. As it goes way this way, what's the height when you get way, way, way over there? Okay. If this one's just growth, don't get paranoid about exactly what does it look like. I don't care. If it's generally growth, it's generally like that. I can write my limit now. I don't need a super detailed picture to write my limits. I just need to know generally, is it going up as you go to the right? Or is it generally getting closer and closer to an asymptote? Like on the left side here, it's getting closer and closer to 0. All right, is this growth or decay? This is 1 minus something. That's decay. So that's shrink. You should know how to draw the sketch, and then from there, the asymptote. Okay, next part. This is asking about writing things in exponentials, and you need to know this form. Y equals a b to the x. If you haven't got this one mastered yet, please write it down and write that this one's the start value, and that's what you always start with. So here, in 2003 it was 35,000 people. That's your start value. So y equals 35,000, and then it's b to the x. Now I got to figure out b. To figure out b, I need to know x and y. That's a point. Something comma something. And this other number here, which you can't see at home, but I'll read it to you, is 38,500. And the time that goes with it is 2007. I could very easily see somebody thinking it was 2007, comma 38,500. But it's more important to note that it was 2003, and now it's 2007, and that's 4 years. So the point they're really giving you is after 4 years, comma, you have 38,500. That's the point that you should put in. It's 4, comma, 38,500. Now, where do you put it? The x is 4, and it goes here. 4 goes in there. And then 38,500 is the y, and it goes right there. And then you solve for b. Your final answer on this guy is going to start like this. Y equals the start value, which was 35,000 people. And then you eventually solve for b, and you get something like, I don't know, 2,800 over 3,650 all to the 1/2 or something like that. You got to solve for b yourself. I don't want to do the whole problem for you. You have to take this and solve for b. Once you got b, it'll be some crazy looking thing like that. And then what part don't I have that's really important? The x. The x and the x. I'd recommend you put it on top, or you say 1/2 x. And it isn't necessarily 1/2. It could be 1/3 or 3/4. This part right here, you have to figure out b by sticking in that point here that I just showed you, in for x and in for y. Now 50 is basically the same thing. You just got to figure out what the 2 points are they've given you. And then you use y equals a, b to the x. And we have made it to the last pre-calc problem. You still have obviously something to do at home, but this is the last one in the pack. Okay. You need this again, y equals a, b to the x. Except this time there's another option. Y equals a and then 1 minus the rate to the x. Because if they give you one like this, where the rate is increasing at 17% per year, you could not just put in b as 0.17. That would mess you all up. I recommend you use not this one, but that you use this one. And if it's increasing at 17% per year, you go 1 plus 17, or 0.17 actually. 1 plus 0.17 there. And I even know the starting value. Starting value is 5. I can just put a 5 right there. And I'm done. That was it. That's how easy those are. If you have questions, you can ask. I'll clean it up. It's A. And instead of B, we just use 1 minus the rate, or 1 plus the rate. Depends. If you want it to grow, you'd say 1 plus the rate. If you want it to shrink, you'd say 1 minus the rate. Yes, sir. Good question. None of these are those half. Oh, wait. Here's a halving. Halving once. If it's half-life, or if it's a doubling or tripling, you want to do those by saying in years, in weeks, in days. Okay, so this is a halving once, that's half-life. So I'm going to go y equals starting value, 592. And then this right here is the key. And it's every 6 years. Here's my time. And I go divided by 6. And then half. How do I do half? Well, I could do 1 minus a half, or is it 1 plus a half? It's cutting in half, so we got to go decaying. And then what do I need? The last thing you said? In years. And that kind of problem. What's different is because it happens every 6 years. All right. The last one. It's got these 2 points. The only thing that I don't like is that by now you may have forgotten the original directions, which say exponential equation, which means it has to be y equals a, b to the x. You can't just use that y minus y sub 1 equals m times x minus x sub 1. You can't just use the one for 2 points. These are special points because they are on an exponential. And so this tells you it's the start value by saying 0, 4. It's saying if I start at 0, I must be the start. So the start value is 4. So the 4 goes right there. And then this point for x and y goes in for x and y, and then you can solve for b. I'll leave you the fun of finishing that off. All right. Congratulations. You've made it through what many of you would probably say is the hardest math class you've ever had. For some of you, it's the hardest math class you will have ever had, because you don't have to take any more math that's really hard. You could go to something easier next year if you wanted. But if you're going to calculus or calculus or AP calculus, then you've got a good foundation, and many people say that Precalc is similarly hard to AP Calc. Really, AP Calc is not. It is hard, but it's not like incredibly like so far beyond this tough stuff that you do. So AP Calc does go fast. There's a couple times where we were able to spend an extra day. You know, I'd be like, hey, today's kind of a review day. You remember those days? Yeah, you don't get those in AP Calc. They pretty much don't have a review day. is keep going. So they have to rush and get done by May, so that after May they've taken the AP Calc test. They just have like a little project. They have to finish their calc up like a month and a half early. That's the good part about taking AP Calc. You get it easy. All right. Any other last questions before we wrap it up? You can always ask me individual questions. Okay, I'll stop the video here, and you have a bunch of time left where you can come up and ask me questions. Almost over an hour of our last review day here. Is it for the video or? Okay, so that's all I have for the video for today.